Thank you very much. So you heard a lot about length scales. So Elenia was on the big length scale, and most of the stuff you heard about up to her talk was on the small scale atomistic. I kind of fit in between. And that in between has to do with phase field methods. And so I want to show you first talk a little bit about how phase field methods work. But I really first should start with acknowledgments. And so this is work that has been done primarily, it's no one. Yeah, okay. So primarily with Jin Zhang. So he's been the driver, So Jin has been the driver for the work on the dead lithium and the phase field model for electrochemistry. And Alex Chadwick, a former postdoc of mine now at the Naval Research Lab, has been working on the thermodiffusion problem and made some real breakthroughs, I think, in that respect. So without those two, I wouldn't be here speaking. So thank you for that. It looks like a mosquito or something on this case. So let me just. Okay. All right. So what is a phase field method? And for those of you who aren't familiar with the way this works, is that if you consider an interface, and let's say this is, I'll look up here between an electrode and electrolyte, but this could be a liquid-liquid interface or a solid-vapor interface. Interfaces between materials are almost always diffuse in some sense. So imagine you take two liquids, you put them together, they have different compositions, and the composition changes slowly from one phase to another. If you have a solid electrolyte interface, the solid interface is never a completely flat facet. You always have thermal fluctuations. You'll have steps, vacancies, and other things that give rise to diffuseness on some scale. And so if you look at an electrode-electrolyte interface, this is an order parameter that takes you from one to the other. It varies smoothly as you go across the interface. And this length scale depends, of course, on the system of interest. And in many electrode-electrolyte interfaces, this is very small. It's on the atomic dimensions, maybe 3 or 4 atomic layers thick. At the smallest scale, you can put together a very beautiful phase field model for the characteristics of an electrochemical interface. And this was done many years ago by John Geyer, Bill Bettinger, Jim Warren, and Jeff McFadden. And they looked at what happens when you have a diffuse interface between the electrode and electrolyte. And by using the characteristics of the two bulk phases, you could write equations for the evolution of the electrons, anions, and cations in the system. And you could write expressions or to solve differential equations for how these quantities change across the interface. And so this is applied potential. You could see how the applied potential affects the structure of the interface. But the interesting thing is down here where you look at the charge across the interface. It's charge neutral in both phases. You have a Debye layer here, and then you have structure within the interface that changes as you change the potential. And so the locations of the minima, for example, in the charge distribution change as you change the distribution of the charge. And so you could have basically a phase field model for the details of what's going on at the interface between an electrode and electrolyte. And this, in principle, makes contact with some of the atomistics that we saw earlier in the week. There's some problems. So I should mention the really great things about this. You reproduce Gooey-Chapman and Debye-Huckel theories. You get the differential capacitance and surface charges exactly with what you see. We did something similar for oxides on a metal, where we were looking at the growth of passivating oxide films on a surface corrosion problem. Same idea. So there's a problem with this approach, and it's not that the physics is wrong. It's that the length scales are a real problem. So you think about how big this length scale is. So this is on the order of nanometers at most. And you look at the structure in the interface, and you can see that you have some rather dramatic wiggles along in the interface. So you have a boundary layer that tells you something about the interface, and then within the boundary layer, you have other boundary layers as well. And so this comes out to be an extremely computationally challenging model when you want to look at dendrite formation, which is something that happens on the micron scale. It's basically not computationally tractable. You have to do something else. And so the game here is, how can we reduce this microscopic model that you see here to a more macroscopic model that you can use to model things like dendrite formation in batteries. And we do that by playing or changing how these interface widths are viewed, but still making sure that we capture the basic physics of what goes on a smaller scale.
Excuse me, may I ask a question? What do you mean by explicit treatment of electrons? I mean, you do not do quantum mechanics. So what?
You don't do quantum mechanics, but you have, for example, the Fermi level in the metal and the Fermi level.
Yeah, but the Fermi level is just a potential for the
right.
potential. I mean,
right.
it's a very classical picture of.
Yeah, and then you have to solve with a double layer at the interface as the potential as you using those as parameters.
Okay.
In the model.
Thanks.
Yeah. But the double layer comes out, which is why you can make all the contact with the electrochemistry, which is really important. Okay, other questions? Okay. So this brings us to lithium batteries. And I'm going to be looking at lithium, what's called lithium metal batteries, which is a battery, luckily not in your Tesla, but it does have some similarities. And the similarity is that you have a cathode and an anode, and you charge and discharge to charge and discharge the battery. And because both of these are both lithium, it's particularly prone to a number of failure mechanisms. One of them is dendrite formation, which is formed when this lithium, when you're charging, the lithium metal undergoes morphological instability and forms long needle-like things. When this touches this, you get the fires we heard about earlier today, which is not something they want. It shorts out the battery. The other source of degradation in these batteries is what's called dead lithium formation. And this is basically a loss in the Coulombic efficiency of the battery associated with the fact that, for some reason, these long things that look like proto-dendrites perhaps break up and form isolated lithium. And since it's no longer in contact with the anode, it isn't electrically active, and it degrades the performance of the battery. And so we'd like to have some idea of these degradation mechanisms because they address these important problems in batteries. And so I'm going to look primarily at two things: the dendrite growth problem and the dead lithium formation. We've been doing some work on SEI formation, which is important as well, but I won't be talking about that today. No. Okay. So it's as you probably guessed, it's a fairly complicated process. You have both the battery charging, discharging involves long-range ion transport diffusion due to classical chemical-driven diffusion, but also migration due to the potential gradients. The interfacial reactions that allow the interface to move are nonlinear. I'll tell you that in a little bit. And they're interfacial discontinuities. And so the whole problem of the double layer in this case has been squashed to a thin interface in this case, where there's a jump between the potentials of the solid and the liquid associated with the double layer. And of course, the concentration of lithium jumps at the interface between the lithium and the electrolyte. And so we'd like to develop a phase field model that will describe this process on a scale that would allow you to do address the problems I mentioned before of dendrite growth and dead lithium formation. Oh yeah, well, one other thing I want to mention. In particular, we want to be able to make quantitative predictions. And the really interesting thing about phase field models is that it's very easy to write down a phase field model. It's very hard to write down a phase field model where you can actually make quantitative predictions and do the real problem. And so I'm going to be emphasizing that last bullet item. And so we need state variables that we have to define here. One of them is this phase field, an order parameter that tells you as you you go from the electrolyte to the electrode. The concentrations in the lithium and in the electrolyte change, and the way we do this is that we have these fictitious concentrations that exist in all the phases. This is a phase field model, so it's valid in all points in space. But the actual concentration, the one that we're interested in, is this dashed line here. And the electric potential is the same thing. We have potentials that are the liquid that's in the solid that's in the liquid, but the real potential is this dashed line. The advantage of this model is that we're not applying boundary conditions on an interface whose shape and location we don't know. We're just solving one partial differential, a system of partial differential equations that holds in all space. And we capture the relevant physics of the problem that we're interested in. So we write a Helmholtz energy. That's a function of the order parameter, concentrations, and potentials. So the bulk energy looks like usual chemical energy. That's the chemical potential times concentration. You have electrical energy. And you can put in other things too, as well. Mechanical energy is very important for solid state electrodes, electrolytes, for example. And the total energy of the system involves all of these terms. There's the bulk energy here. This is an interpolation function that interpolates between the electrode and the electrolyte. These are the energy, the Helmholtz energy of the particular phase of interest. The interesting thing about the phase field model is that you pick up a normal term here that involves the order parameter, but you have gradients in the order parameter. And that turns out to be important because those gradients are what set the interfacial energy in the problem. And so it's a relatively simple model here. You say that you choose the constitutive equation such that the energy decreases with time, which is what the second law says. And you end up with a set of equations that look something like this. This is just a repetition of what I showed you before. These are the interpolation functions that take you from the solid to the liquid. 1 in the solid, 0 in the liquid. And you take the variational derivatives of this function, and you say, well, the energy has to decay in time, and so that each one of these terms has to be non-positive. And in particular, if we focus on this one, and this is the variational derivative of the Helmholtz energy with respect to the order parameter, in other words, the location of the interface, times the time rate of change of the location of the interface. And the reason why that's important, this term here, is it allows you to define the over potential in a thermodynamically consistent way. That is simply the variation in the Helmholtz energy with respect to the position of the interface. You know that the time rate of change of the location of the interface is related to the charging. That's straightforward. And therefore, second law says that this product has to be positive, that the over potential times the current has to be greater than or equal to 0. And that's it puts a constraint on the constitutive laws, but not a terribly difficult one, because you can see that all three of those that are used often in practice satisfy that thermodynamic constraint, but they're nonlinear. The Butler-Vollmer and the Marcus models for the relationship between the overpotential and the current at the interface. And so if you want to look at what the overpotential is in the classic sharp, or what we call a sharp interface case, where you don't have a diffuse interface, the overpotential involves the interfacial energy times the mean curvature. It's a curvature effect. And this is the kind of standard Nernst-like equation that you see in the battery literature. This is the jump in the potentials at the interface. This is the jump in concentrations at the interface, and we're making some assumptions that we're in the dilute solution limit thermodynamically in the electrolyte for the concentrations. The phase field model resembles this somewhat. The interfacial energy term sits here, and the bulk, the activate overpotential sits here. But these quantities now are defined at all positions in space, and so they're not just sitting on the interface itself. So we have to have a model for what goes on at the interface. We just use a simple Helmholtz double layer, but we can, of course, use other models as well if we wanted to. But we started with a Helmholtz double layer at the interface. So there's a problem. So this model is relatively straightforward to write down, relatively straightforward to come up with the constitutive laws that satisfy the second law. And you might ask the question, why haven't people done this before? It's because whenever you do this and you apply this to a real system like lithium lithium cathode anode in that electrolyte, 1 molar lithium phosphate. System size on the order of 100 microns. What you find is that you start with an interface between the lithium and the electrolyte that looks like this green line here. You allow the system to evolve, and what happens is the interface actually breaks up. It becomes unstable. And it's unstable because in these electrochemical systems, and if you're doing oxidation of metals, it's the same thing. The chemical driving forces associated with electrochemistry are so large compared to many other systems that these interfaces become unstable. And how do you get rid of that problem? Well, you get rid of that problem by making the interface thinner and thinner and thinner. And as you make the interface thinner and thinner and thinner, you get to the point where it becomes stable and you don't have to worry about it breaking apart. And so this is an idea of how the grid size necessary to resolve this interface in a micron scale system size of 100 microns, versus the voltage that you use to charge. This is in millivolts. And you can see that when you're pushing the system pretty hard, you're at large voltages, your grid sizes are on the order of nanometers. And so you're very quickly back to the problem where the interface thickness is on the scale of the real interface thickness, which makes the problem completely computationally intractable. You can't do it because you have to do something on the micron-like scale. And so how do you handle this interface where you have this instability that you deal with? And so what people often do in the phase field literature is that they ignore this problem and they just do unrealistic simulations. It happens all the time. We were trying to do realistic simulations. So what the problem, it turns out, is that the overpotential through the interface is what's causing the instability. And you can, and to get rid of that, we have a driving force extension method, or activation overpotential extension method, where you write the equations using a projection of the driving force along a normal to the interface. And this allows you, instead of the actual eta, to use this projection, and it gets rid of the instability, and I'll show you in a second. And it's based on the fast marching method, so anyone who knows level set methods is familiar with this. The technology to do this is very well developed, and so this is very fast. And Dave Chop, who is on this paper here, wrote a version of the fast marching method for a parallel code too. So we have a parallel version of this is working too. So what happens is, this is the original overpotential as you go through the interface of length L, and you can see that this will in fact be uniform if you make this smaller and smaller and smaller, and you access this nice uniform region. If you use the projection method, you get this. So it's uniform, and you get around the problem with the interface splitting into multiple parts. And so it's applicable for systems that have large driving forces at the interface, large interface reactions. And so this is what I showed you before. This is kind of state-of-the-art methods with extremely small grid sizes. At this very high potential, this is where the driving force extension method comes in. So it's stable all the way up there in this unstable region. So for a typical time step that scales like the square of the mesh spacing, which is what you would have, this is second order space equations typically. So if basically it allows you to increase the spacing by an order of 1,000, and it reduces the time by about 10 to the 12th or 10 to the 15th for a particular calculation. So this is a rather dramatic increase in the execution time of the code, and allows us to do both 2D and 3D simulations. Using this trick that we're not following the real interface thickness, but we do it in a way that we're getting the right answers. And so I'll show you that in a second. So these are the PDEs that we're solving. We have an evolution equation for the location of the interface as proportional to the current. We have a diffusion equation for the ions in the electrolyte. This is the electrochemical potential here. And then you have ionic charge conservation and electric charge conservation. And you can see that these are the normal kind of equations you might expect to see. You have source terms on the other side associated with the motion, rate of motion of the interface. So as the interface moves, ions go in or out of the interface, and that's what these terms basically capture. And so those are the 4 PDEs that we solve. And you want to be sure that it captures what you expect is what are called the sharp interface results that you would get from classical electrochemistry. So this is the voltage as a function of concentration that you would expect from the Nernst equation there, and it agrees quite well. So this, the points of the phase field method. And you get the curvature effect quite well by looking at a curved metal electrolyte interface, and that does quite well. It turns out this curvature effect is very important because this provides the stabilization of the regularization of the PD, so you have to get that right too. And you can use various kind of reaction kinetics models, and so one of them is the Marcus model. This is the agreement between the phase field and the Marcus, and the other one, even more complicated, is the Marcus-Lefschizely, and we get a very good agreement with the overpotential and current density there. So it's a relatively general model. It agrees with classical electrochemical chemistry, so we can do the calculations in a way that we think we're going to be getting realistic answers over realistic length scales and time scales. So this is a charging of lithium. This is a lithium interface here. These are the flux lines. And as that grows, you can see that the lithium, quote unquote, dendrite forms by concentrating the flux at the tips of the regions. You can see there's very little flux down here. It's all being directed towards that object at the top. And that's what gives rise to one of the failure modes of lithium metal anode batteries and regular batteries as well. And so if you're worried about the parameters we use, they're reasonable parameters for a typical battery. The domain size is about 128 microns this way, and about 64 on the other side. And it's a parallel code. It took 12 days over 52 cores, which is a pretty small calculation. So what about dead lithium formation, and how does that work? Well, what you find is that the dead lithium in particular appears after you go through many charge-discharge cycles of the battery. And so this is the current as a function of time, charge and discharge, and the voltage varies with time to drive that current. And we started a system here. This is the applied voltage. This is the lithium metal. That's the electrolyte. We started with a little perturbation at the top, and you will watch the charge and discharge cycles. You can see that the system's undergoing charging and discharging. You can see that the voltage is decaying, which is not something that you want associated with these charge and discharge cycles. But the nice thing about the phase field method is that topological transitions are not a problem. And look at the roots of that dendrite as a function of time. Eventually, the roots of that dendrite will touch. And the calculation will stop, of course, because that's all we're interested in. But you can see that it's almost there. There it goes. And it's created a little region of isolated lithium from the dendrite. So the question here is, what gives rise to this asymmetry? You expect charging and discharging to be completely symmetric, right? You charge for a certain amount, you discharge. It goes back and forth. That's obviously not what's happening. And what's the source of the asymmetry? And we've done these calculations in 3 dimensions, but you can see the same thing in dead lithium formation. So if you look at the current as a function of position during plating and stripping, in other words, where you charge and discharge, you can see that it's in fact not symmetric. And so the change in the current for plating is not equal to the change in current from the stripping, and it's associated with the fact that the concentration dependence of the chemical potential is nonlinear. And the concentrations aren't exactly in the neighborhood of the stripping, are exactly different, are not exactly the same as in the neighborhood of the plating. And they're not hugely different, but when you cycle the battery many times, it becomes important. And so you can look at a parameter that we defined to kind of get some idea of what's going on with the dead lithium formation. Why does it form? And it's the applied current divided by is a parameter that we dreamed up. That Jen dreamed up. That's a difference between the plating and the stripping current. So if it's exactly symmetric, S is infinity, and if this is non-symmetric, it's order 1 or something that's not infinity. So you'd expect to see no dead lithium when it's very large, S is very large, and dead lithium present when S is very small. And so this is the symmetry parameter. These lines here are the symmetry parameter as a function of the applied current relative to the limiting current. This dashed line here, which is the symmetry parameter, is from linear stability theory of a planar surface, which is, of course, nowhere near dendrites. And this is the symmetry parameter that comes out of the phase field model, and it agrees pretty well, so amazingly enough. And so when the applied current's on the order of the limiting current, in other words, you're running the battery, you're charging it as fast as you can, the symmetry parameter is quite small. It's approaching quite small, which would give you which would mean that you'd tend to form dead lithium down here. But when you're not charging it so quickly, the symmetry parameter is very big. It's going to infinity, which means you tend not to form the dead lithium. And the time to pinch off and the symmetry parameters that you get agree quite well with the phase field method for various exchange currents. You see up there. The model does not work, I would say, when the applied current is very close to the limiting current, because that's really a pathological case where you have almost no solute concentration at the interface. So you can compare to experiments. So since we have a linear stability calculation, we know what the parameters are that go into the symmetry parameter. And you compare the symmetry parameter, which we get from the linear stability theory, with the Coulombic efficiency that you get from experiments for a given set of electrolytes and applied currents. And consistent with what we see in the theory, for higher applied currents, the Coulombic efficiency decays, which is why they like to charge batteries slowly. On the other hand, and it agrees very well with this particular electrolyte. With this one, it doesn't. And we think that at the very large currents, at least, it doesn't agree very well. And we think that's associated with the SEI formation for this particular case. There's been a large discussion in the literature about what the effects of the exchange current are on the Coulombic efficiency. Some people say the higher exchange current gives you better Coulombic efficiency, or vice versa. It turns out that because the symmetry parameter, which is what we get from our theory, is a function of close to 5 materials parameters beyond just J0, that in order to get a correlation between the symmetry parameter and the Coulombic efficiency, you need all of these parameters. And when you do that, you get a pretty good agreement between the Coulombic efficiency and the symmetry parameter, except in one case where the solution was a very 7 molar, which is a very concentrated solution. It doesn't correspond to our dilute solution approximation. And so what this does is it gives an experimentalist a handle on when to expect to have a low Coulombic efficiency battery. One of the nice things about the phase field method is that you can do nonlinear things. So you can look at the effects of dendrite formation in various domains and the interactions between dendrites, which is not something that you get from just looking at a single one. So this is the base case here, where you start with a perturbation and it evolves to a point there, a pinch-off, which is dimensionless 116. If you change the initial perturbation, you make it smaller, it takes a little bit longer. If you change the size of the domain, in other words, change the initial wavelength, the curvatures increase, and so it's still a smaller time. And then you can look at interactions between perturbations and how that develops. And it does have an effect. In one case, you don't see pinching on one dendrite, but you see it on the other. But the point is that they all kind of sit in about the same kind of time scale. So we're getting about the right answer, even for complicated shapes. And so one thing I will mention, and I want to make sure this is clear, is that this pinching process here is not a Rayleigh instability, right? It's not a Rayleigh instability. It's due to the asymmetry in the electrochemical stripping and plating. And so we have basically takeaway messages for the battery designers. You want to stay away from the limiting current. You want to keep the concentrations from depleting. Slow charging or discharging, well, that's obvious, but you don't want to do that. High electrolyte concentrations help. High diffusivities help. High diffusivities, lithium diffusivities. And asymmetric reaction kinetics can also affect the process. Lithium is not an isotropic material, and because of that, you have the effects of crystallography on the evolution of these dendrites. And so this gives you some examples of cases where you can see that you have changes in the shapes of dendrites that are consistent with the crystallographic orientation of the solid. And so in one case, it looks relatively isotropic. In the other case, it looks highly anisotropic. And this is a function of the charge rate as well as the electrolytes. And those are from the papers down there. And with the phase field model, it's relatively easy to put in anisotropy. So you can have anisotropy in the exchange current, which has been measured in some systems and not necessarily in lithium. And you can have interfacial energy anisotropy in the interfacial energy. And using both these two effects, you can look at the effects of crystallographic orientation and anisotropy on the evolution of the dendrites, and how does that affect the dead lithium formation process. And so here we focused on the exchange current because the exchange current is a very strong anisotropy, very anisotropic. This is the isotropic case. You can see that you get from here. In the anisotropic case, you see that it pinches. You can see the anisotropic-like shape. But if you orient the crystal such that the J0, that the crystallographic orientation of the solid in contact with the electrolyte is 110 in this case, you get almost no dendritic like process. And so it's quite clear that the orientation, in this case the 110 plane, because of the lithium, has a major effect on the evolution of the microstructure. And it would be helpful to really have a good measure of this anisotropy in the exchange current. Okay, so thermodiffusion and thermodiffusion is a rich area. It's been studied a lot, but normally it doesn't have any effect in many cases in the materials processing situations. But what they found in batteries, if you take a symmetric cell and you put a temperature difference across the anode and the cathode, what you find is that cell lifetime's improved when the warmer electrode charges first. And this change in temperature across the cell is small. It's on the order of 1 Kelvin. So it doesn't take a lot of a temperature change, and that can promote or suppress dendrite formation. So the thing that's a little strange about this is, why would a 1 Kelvin difference between the anode and the cathode affect the evolution of dendrites? Normally you have thermally activated processes. 1 Kelvin's going to affect it, but not that much. And what Alex Chadwick recognized is that a 1 Kelvin difference across a 10 micron spacer is a temperature gradient about 10 to the 5th Kelvin per meter. And so that small difference in temperature produces a large temperature gradient. And the question here is that can this large temperature gradient drive mass and charge in the electrolyte by the Soré and Seebeck effects? So can you have mass diffusion driven by temperature gradients enough to affect the stabilities of interfaces? And so you go back to the sharp interface descriptions of diffusion. So you have the classic diffusion equation here, but you get extra terms now associated with the temperature gradient. So this is the Soré coefficient, which normally requires very big temperature gradients in order to have an effect. And then you have the gradient, the transfer number, dotted into the ionic flux, and there's the Seebeck effect, Seebeck ion coefficient as well. So the evolution of the concentration field now is coupled to the temperature gradient, as well as to the potential and the gradient and the concentration, as you might expect. But obviously, these two things can have an effect. And where do we get these things? Where do we get the Sorey and ionic, Sorey coefficient and ionic Seebeck coefficient? And what we've done is molecular dynamics simulations. And so this is an example of how you can use first principles calculations to provide the parameters for a phase field model. And you get a multi-scale model that way. We did a sharp interface analysis as well using linear stability theory, as I'll show you in a second. So the effect is kind of illustrated over here. We have a discharging and charging interface. Here's the lithium interface down here. So you have a flux of lithium going from this side to this side. So this is temperature gradient. This is the diffusive lithium flux that varies slightly with temperature because of the slight thermal changes in the properties of coefficients. The diffusion coefficient can be functions of temperature. That was calculated. This is the applied current. And so the difference between these things are made up by the migration flux associated with the potential gradient and the thermal flux associated with the Sorey and Seebeck effects. And you can see that this flux due to the thermally generated, to the temperature gradients, is on the same scale as what you would see for the migration. It's kind of even on the same scale as the diffusive case. And in fact, it changes sign as you change the temperature gradient. And so it matters whether the temperature gradient is positive, negative anode cathode, or negative positive anode cathode. You get different fluxes and different evolutions of the interfaces. And these are using the parameters that come out of the molecular dynamics. So these are, in principle, reasonable estimates for what those coefficients might be. And here's a measure of the temperature gradients from 500 to 1,000 Kelvin per centimeter. So you could do a linear stability analysis of a planar interface. So this is the growth rate of the instability. Sigma here is the growth rate, K is the wave number. This is the initial height perturbation of the interface. So here's the wave number, growth rate here. The solid lines are what comes out of the linear stability analysis. You can see it's on the order of micron scale wavelengths for various temperature gradients. So the base case here is 0 Kelvin, which is this one here. And you can see there's a band of unstable wavelengths, which tells you that the interface is unstable, and you get the growth of perturbations. If you put a positive temperature gradient across it, it increases the growth rate of the instability and increases the range of unstable wavelengths to the Kc is the critical wave number, where sigma is equal to 0. If you put a negative temperature gradient on it, you get the green curve here, and it stabilizes the interface. In fact, if you put a negative 1,000 for the particular parameters we chose about it, negative 1,300 Kelvin per centimeter gradient, you have the critical gradient at which you get no instability at all. So you can completely suppress dendrite formation by putting a big enough temperature gradient across the anode and the cathode. It's big, but in principle, you could do this. We also did phase field calculations. And so the solid lines are the linear stability analysis. The points are the phase field calculations for the exact same parameters. So again, we're sure that the phase field model is actually doing realistic simulations in the sense, simulations in the sense that for realistic parameters, the phase field model is agreeing with the linear stability analysis. And so we're quite confident that the results make sense. And so if you look, for example, at the critical temperature gradient, which is the one that gives you a curve that looks like this, a dispersion curve that looks like this, where everything is stable, it's a function of the temperature gradient, the applied current density, and the value of for example, the ionic Seebeck coefficient. And you can see that as you go to higher current densities, to get stability, you need bigger temperature gradients. And so that are harder and harder to perhaps attain. But nevertheless, for reasonable values of the Seebeck coefficients and reasonable temperature gradients, you can actually stabilize the system. But what the takeaway message from this is that these thermal effects are more important for small applied current densities typically than what you would see in experiments. So the nice thing about the phase field model is that it's possible to do nonlinear calculations. And so here's a first panel over here. This is the charging rate, minus 5 amps per meter squared. Negative temperature gradient, isothermal, positive temperature gradient. And so the prediction is that the positive temperature gradient should be more unstable than the negative temperature gradient. And this is the current as a function of position here. So it's obviously charging faster at the peaks than it is at the troughs in the isothermal case. And this would give rise to faster growth at the peaks of the troughs and dendrites. So let's see what happens if I... So as time goes on, the system becomes unstable. And you can see that in the positive temperature gradient case, it's more unstable. You get very, very deep grooves, very, very sharp peaks that are bigger than what you see in the isothermal case. But if the temperature gradient's reversed, you can see that the amplitudes of the perturbations don't change very much at all. And they do not develop like you would have in the positive case or this case. If you charge faster, so in other words, if you had still a larger current, you get something that looks like this. And there's not a huge change from one panel to another. In other words, the temperature gradient might be having an effect, but it's not enormous here, and it's because it's dominated by the charging current, the migration of the atoms due to the potential gradients. Oh yeah, one other thing I'll mention is these are in a moving reference frame, so actually this is moving with the charging and discharging interfaces. So these are actually moving. It's in a reference frame associated, that's stationary with respect to the average position of the interface. So the takeaway message is, well, gee, it won't stabilize the system, but what it does do is that even if you have perturbations, you can see they're not developing at the rate that you see in the isothermal case. So things that are non-planar will tend to stay non-planar and not run away like you would see in the isothermal case. But it's most important for cases where you have smaller currents. Okay. So what I've shown you is a phase field model can be put together that allows you to do realistic simulations of electrochemical processes, and we've applied it to batteries. One of the surprising discoveries of this was that this asymmetry between charging and discharging seems to have a key role in the formation of dead lithium. And that even though thermal gradients are thought to be relatively insignificant in many cases because of the small size scale of batteries, you can have significant thermodiffusion that affects the growth of the dendrites and the planarity of the interfaces. And from an applied battery design standpoint, what it says is that the thermal management of the system, the directions of the heat flow, the temperature gradients affect the stability of interfaces and whether or not you get gradients. And so that can be part of the battery design process on the scale that Elena talked about earlier today. So with that, I'll end, and I'll be happy to entertain questions. So thank you very much.